Hello, continuing our work with proof by induction, we are going to be looking at inequality type proofs. So the steps will be identical, but we're going to have to do a slightly different job to get all of the marks. But again, the same is true as has always been true. The first 50% of the marks are very straightforward to get and everyone is going to get them. And then we will look at how it is we finish off the question after that. But we all know what we're going to do here first. We're going to show that this relationship that we've been asked about. So we want to prove that 3 to the power of n is greater than 2 to the power of, 2n plus 2. Now, we have a restriction here that we didn't have listed much before. N is going to be greater than or equal to 2. What effect does that have? Well, so far we've been saying in part 1 that n was going to be equal to 1. That was going to be our first test, our first step. But in this case, because of this restriction, the smallest value of n we can pick is 2. So therefore, we're going to have n is 2 is going to be our first step instead of n is 1. So we have to always look at restrictions when we're doing the exam papers because they are often critical. So this restriction here is coming in that we're using n is equal to 2 as our first step as opposed to n is equal to 1. So I sub in n is equal to 2, my smallest value of n, and I'm going to end up with 9 is greater than 2 by 2 is 4, plus 2 is 6. 9 is indeed greater than 6, therefore my relationship holds for my smallest value of n. Part 2. I'm going to state that I assume that this is true for n is equal to k. What does that look like? N is equal to k is assumed to be greater than 2k plus 2. Same setup as always. We've done basically no math so far. Part 3. Part 3, we are going to say if n is equal to k is true, then we are going to have n is equal to k plus 1 must be true. Same setup for stage 3 as always. Now, like when we were doing the divisibility proofs, we're going to start off with the situation where n is equal to k plus 1, and we are going to use this n is equal to k situation to help us along the way. So for series problems, we start out with n is equal to k, and we modify it to show n is equal to k plus 1. For our divisibility and inequality proofs, we start with n is equal to k plus 1, and we are going to use the n equals k result as part of helping us with n is equal to k plus 1. So what we've got then is the n equals k plus 1 position. I'm just subbing in k plus 1 anywhere there would be an n in my inequality. And I'm going to try and get something that's going to allow me to use my n is equal to k situation. Now, what jumps out at me here is I have 3 to the power of k in my assumed situation, and I have 3 to the power of k plus 1 here. I could get a 3 to the power of k quite easily in this equation, inequality I should say. So let's try and rearrange that. If I am adding my powers, it means that I was multiplying the base numbers. So I have 3 to the power of 1 multiplied by a 3 to the power of k. This is the same as this. Adding my powers, multiplying my bases. I multiply out my brackets here. I get 2k plus 2 plus 2. This part here, this is the trick, if you like, of this type of proof. This part here must be greater than, or I have assumed it is greater than 2k plus 1. So 3 to the power of k I know is greater than 2k plus 2. So I know this is greater than 2k plus 2. So if I could show that the following, if I could show that 3 times 2k plus 2 was greater than my right-hand side, 2k plus 4, adding 2 plus 2. If I could show that this was greater than this, and I have assumed that that 3k is greater than this, then I've automatically shown what I want to show here. So this ought to be less than 3 to the power of k. So if I can show that this left-hand side is bigger than the right-hand side here, or if I can find values of k that would make that true, that is going to guarantee that my original left-hand side was bigger than my original right-hand side. So this now becomes a matter of simply solving a basic linear inequality. So I multiply out my bracket, I get 6k plus 6 greater than 2k plus 4. This is just solving a normal inequality. All the funny business is basically done. Minus 2k minus 2k. I don't need to worry about flipping around my inequality here because I'm subtracting and adding. I'm not multiplying by anything involving k. I don't want this 6 here, so I'm going to subtract 6 from both sides. And I end up with 4k greater than minus 2. Divide both sides by 4. And I get k is greater than minus a half. Now, what in the world does that mean? It means that this relationship here will be true for any value of k greater than k is equal to minus a half. Okay? Now, remember, k is a value of n. So what I've essentially shown is that this relationship here is going to be true. This relationship here is going to be true for n greater than minus a half. Why is that useful? Because that tells me for n greater than minus a half, this relationship is going to be true if n equals k, if my assumed relationship is true. So if this is true, then the n equals k plus 1th position will be true for any value of k, or any value of n, I should say, greater than minus a half. And I only need this relationship to be true for n greater than or equal to 2. So I'm sorted, because my relationship, what I need to works for any number for n greater than minus a half, and I'm only asked to show that it's true for n greater than or equal to 2. So I've now shown what I need to show. And I'm going to write out my final step for you now. So we have the standard form of our final answer. As we have shown that n is equal to k plus 1 is true if n is equal to k is true, and we have shown that n is equal to 2 is true, therefore the next value of n must be true. Our relationship must work if n was equal to 3. If n is equal to 3 works, then we have shown automatically that the next one, n is equal to 4, must also work, and so on. Therefore, we have shown that this is true for all values of n. So you can see that the steps are identical for any type of proof by induction. Getting up to this point here in our question gets us 50% of the marks. And in an inequality style question, no matter how they look, you are always going to have something that has a power of n involved in it. You're going to end up with usually k plus 1, and you're going to take out your plus 1 power here and use a substitution of our assumed inequality, and then rearrange and show that the range that this is true for is greater than the range that we need. And that's how all proof by induction inequality questions work. They're always going to be the same. You're going to start with the k plus 1th position. You're going to break up your power as we have done here. And then you're going to say, well, this I'm assuming is greater than my right-hand side over here. And by that substitution, show that the range that this relationship works for is greater than the range that we were originally asked for in the question. That is universally how our inequality type induction proofs are going to work. So in wrapping up this discussion of proof by induction, hopefully now you can see that all of these problems follow a very strict set of steps. And if we follow those steps as far as we're able to, we will definitively pick up 50% of the marks. And if we can get used to the 3 different styles of them, our series, where we add our k+1th position into each side, our divisibility, where we have to break up our numbers cleverly, and our inequality, where we have to do a substitution. If we can learn those 3 different methods, we'll be able to do all of our proof by induction. But the absolute key thing for everyone is we can all get up to this point here, getting ourselves 50% of the marks. There is never an excuse in the exam for not getting at least 50% in the proof by induction questions, because there's no maths up to here. It's just show it for the smallest value of n, assume that you're going to have it work for n equals k, and then write down n equals k plus 1. 50% of the marks in the bag, and everyone should be getting that, even if we aren't comfortable with the next steps. If we can't remember the 3 different things we have to do for our different styles, we can all get 50% in these questions, guaranteed. And then we just take a stab at our work after that. And we have our 3 different methods, and they're very repetitive. But the key thing is no one gets less than 50% in a proof by induction question on our exams. So that is